Hello and welcome to my presentation on artificial blood vessels. The blood vessel that we will be investigating today is the carotid artery. As seen per the picture, the carotid artery is located in between your esophagus. Now, the carotid artery is responsible for blood flow to the brain. Any damages that the carotid artery experiences can lead to threatening symptoms. These symptoms include slurred speech, numbness, and weakness of the body. Now, what type of damages cause the artery to erupt or rupture? These damages can come through a genetic defect, something that's not really in control. Through genetic defect, the artery could either already be weakened or have some sort of rupture, and this will then therefore need either repairment or replacement. An impact to that specific region of the body, to the neck, can also cause the artery to break or to have rips or ruptures, which will then need to be repaired as it can cause internal bleeding. Also, as the body grows older, the artery also grows with the body, of course, but it also becomes weakened through time. And that's something that's similar to genetics, not really controlled. With age, the body grows older and weaker, and so does the artery. Now, the solution to a weakened artery or a ripped artery is to replace it or repair it. This can be done with materials that, through the advancements of technology, are within the realm of possibility to acquire and to make. And to find that adequate material, simulations will need to be ran. Now, the materials in question are polycarbonate, polyethylene terephthalate, and polytetrafluoroethanol. Now, it's in respect, it's of some sort of abbreviation is polycarbonate, Dacron, and Teflon. Now, in the image here, you can see some of the important material properties, which include Young's modulus, ultimate tensile strength, and the price per metric ton. Now, these three factors play a key role into finding which material is going to be best to replace the artificial blood vessel. Now, each of these materials are already in use in the body, but to really find, the best material to use repeatedly and to use on common basis to repair it, is going to be the question that will be answered later on. Now, in order to really determine which material is best, simulations were ran. Now, in SolidWorks, there's this add-on that's called flow simulations. Now, in the flow simulations, each of the materials were ran at different lengths. The lengths include 1 millimeter, 10 millimeters, and 100 millimeters. Now, these help to determine how the blood flows within those materials and how the materials react to it, how the internal stress is, and whether or not it could withstand within these different lengths. Furthermore, to really ensure which material is best, the test is ran at the normal blood flow and 5 times the blood flow as a human experience exciting moments which increase blood flow either to the brain throughout physical activities, nervousness, anxiousness. Now, here are the samples of how the simulations were ran. To the left, you see a drawing, which is of the polycarbonate of the 1 millimeter. You can see the radius, the thickness, and the length of it. And this is more so a sample of how all the different lengths were made. Each all had the same radii and the same thickness, but measured with different lengths. In the right image, you can see the conditions of how the simulation were ran. So with the blue arrows, you see an environmental pressure. Since the blood vessel is within the body, it experiences constant pressure, different than atmospheric pressure. In the red arrows, you see the blood flow flowing. And then this will help to simulate and sort of see the stresses within the blood vessel, whether or not the material can withstand it. Now here you see the raw data. The left image is at the normal blood flow, and the right image is at the 5 times the blood flow. Now, this is just the raw data. You can see it's separated with length, the material, the pressure, and the hoop stress. The reason hoop stress is included in this is because since the blood vessel is a circular vessel, the stress react differently than within a straight plank material. Now, hoop stress, it includes the radius, and it takes into account the different stresses the blood flow can experience. Now, here are the graphs for the normal blood flow, which is 0.08 kilograms per second. From left to right, it's 1 millimeter, 10 millimeters, and 100 millimeters. As you can see, at 1 millimeter, Dacron and polycarbonate don't really have much difference when it comes to relation of hoop stress and pressure. The difference increases, or the difference is more notable as the lengths increase. So at 10 millimeters, you see Teflon experience a high pressure and a high hoop stress, whereas Dacron experiences a low hoop stress and pressure. At the 100 millimeters, you can see that Dacron then experiences a really high pressure and really high hoop stress, whereas Teflon remains on the low side. Here we see the graphs for the 5 times the flow rate, which is 0.4 kilograms per second. As per the last slide, it also increases from left to right from 1 millimeter, 10 millimeters, and 100 millimeters. Here you can see the differences of how the materials react at 5 times the blood flow. From the previous slide, you can see on the 1 millimeter, Dacron experiences the highest pressure and the highest hoop stress, whereas at 5 times, Teflon experiences the most hoop stress and pressure. And at the 100 millimeters, you can see that Dacron and polycarbonate experience almost about the same, where Teflon experiences the least. And that's very different from, or sort of similar from the normal blood flow, where Dacron experiences the most, polycarbonate the highest pressure, and Teflon the least, and the same for the 5 times, where Teflon is also again the least. Now, this slide is about the materials of the price of the materials that are in question. As seen, you can see that Teflon is the most expensive, then it's polycarbonate, and the least expensive will be Dacron. It is important to know, as it can help determine which material will be used more commonly in hospitals to replace the carotid artery. And with those key factors in mind, Dacron will be the most useful and the more convenient material for the blood vessel. Now, per the experiments and the simulations that we ran, Dacron experienced a max pressure of 0.021 megapascals, which is it's not notably larger or smaller than the other materials and what they experience. So they all sort of experience the same amount max pressure. And with that in mind, it is also important to note that it does not exceed the Young's modulus or the ultimate tensile strength. This is important to note, as it can help to reassure that Dacron does not erupt under those conditions, which include the pressure 5 times the normal blood flow, and the temperature within the human body. And because it's also the cheapest out of the 3, it's also easily acquired, easy to get, and furthermore, it solidifies itself as the best candidate for the material. Thank you.